In this module, we're going to talk about Newton's second law and from where do we understand this. Okay. First things first, I cannot tell you how to prove Newton's laws because even Newton can't do this. Okay. For this, you need to understand how science works. How science works is we define a framework within which we can ask questions, and that framework for us is Newton's laws of motion in this case. And these laws are what we call axioms. These are axioms, okay, and these are statements which are guesses. Okay, in science we call these guesses hypotheses. This is a guess, okay, and Newton's second law that we have stated before, I have stated for you before in the previous modules, F equal to ma is a guess about how the real world behaves. Okay, and why do we believe it then? Because when the observations match this, then we strengthen our belief in these laws. Okay, so today's module is about how to wrap our heads around this law. Okay, and also how would have Newton come upon guessing them? We'll try to guess that. Okay, to guess that, let's dissect this law a little bit more. Okay, F equal to ma, like I told you, a is acceleration, which you already know. Okay, and force is something new that Newton hypothesized to exist such that it causes a change in the velocity of a body. But how does mass also come into the picture? Okay, to understand this, I'm going to introduce you to a more basic version of this law. Okay, to understand that, let's take up this example of a flying rat and a flying elephant. Okay, why these examples? I'll come to it. Okay, what I'm trying to do over here is me being like a 16th century crazy experimentalist. Yeah, I'm making all that up. Is using a catapult, okay, which can exert. I know that it's like me, yeah, and I'm given a task of kicking as hard as I can, and I have two balls in front of me. One is, say, a basketball or a football, which is pretty light, and another is a bowling ball. This is made of metal. This is pretty heavy. You know that. Okay. Now I have some max power. I have some maximum. I'm using this word power in a very English sense. Okay, not a physics sense right now. Yeah, I can kick only that hard. I kick both of these equally hard. Do I expect? Does my common sense tell me that both will go equally fast because of this? No, right? No, right? Similarly, if this catapult has a maximum level and I use it to throw a rat and to throw an elephant, yeah, I don't expect both the elephant and rat to go flying off at the same speed or same velocity. Okay, I expect it to depend on mass. Okay, so I being Newton here, dream a new quantity, which is mass into velocity. This is called momentum. Okay, and strictly speaking, this momentum is vector because velocity is a vector, and when you multiply a scalar and a vector, you get another vector. Okay, so this quantity momentum I am defining because I think the state of motion of a body is not married only to its velocity, not married only to how fast this is going, but also married to how massive it is. Okay, how massive it is. These two are both related to the cause and effect relationship. Okay, so I define this mv. Okay, I define this mv, and I say, and I postulate that to change this mv, to cause this change in this new quantity called momentum, it's called linear momentum. It's called linear momentum. Why the word linear? Is because this is for a point object, Yeah, all these laws are for a hypothetical point object which is going to move in a particular direction. Okay, for extended bodies there's another kind of momentum which I'll teach you later. Okay, so yeah, so we saw that for anything to change its velocity, a force is required. Okay, that's what Galileo, that's the legacy of Galileo. But what's the new thing Newton thought here is that the change in this quantity called momentum is what should be caused by force. So force should be directly proportional to this change in momentum. Okay. And what's the second thing? What's the second thing he observed? The second thing that we are trying to guess. The second thing is that it's not only the change in momentum that the force depends on, it also should depend on how fast this momentum itself is changing. Okay, in other words, you would have seen this very famous example of a fielder trying to, I don't want to get hurt. That's what he's trying to do. Okay, he's trying to catch a ball that is flying towards him with some velocity. Okay, it has some mass, so it has some initial momentum. Okay, when he catches it, it's going to come to rest. Yeah, so there's going to be some delta p. Okay, now think about your experience of playing a sport like cricket or baseball or some sport which is ball and bat based, or just catching a ball. Yeah, even that works. Okay, in case you change the momentum really fast, if you're a pathetic catcher like me and you do this really quickly, you'll get hurt real bad. Huh? And what about some great sports star that you appreciate? Okay, will he also get equally hurt? You don't expect that, right? They can take a lot of catches, and yeah, you might have also learned a little bit. And what is taught to you? Can you affect this delta p? Can you change this? Can you change this? Think about it for a second. This V is because of the batsman or whoever threw the ball. Yeah, this is going to be what it is. And once it comes to rest, the momentum is going to be zero. So this delta P is same whether you're pathetic like me or a superstar like, I don't know, whoever your favorite superstar is. But what is changing? What is changing is time. Okay, a good catcher will take more time so that he does not experience more hurt, and hurt in physics should be linked to force. Okay, so this is not the whole picture, and there should be a delta t in the denominator. Okay, the one that comes below. Okay, so force is proportional to change in momentum by time. That's what Newton's guess was, and that's what we have been using as F equal to ma. So how did this change its form to our famous equation? Is this F is proportional, and you can get rid of the proportional sign for equality, because this translates to F equal to k delta p by delta t. And yeah, what's the unit of force? You would have learned in some previous standard itself. It's Newton's. Why? Because Newton discovered it, and when you discover it, when there is nothing called force before, you get to choose the value of this constant. Okay, this constant k, and chose it to be 1 for simplicity. Because otherwise what would have happened? Today I know that 10 Newton force, if there is 1 kg mass, will cause 1 meter per second square acceleration. Okay, if Newton was the saddest person who said this constant should have been, say, 10,000, okay, then 10,000 would have come here, and this force would have become 10,000. Okay, then 10,000 Newton would have meant that if I kick with 10,000 Newton force, 1 kg ball will get accelerated by 1 meter per second square. Yeah, if it's 2 kgs, what would have happened? To 20,000 Newton. Now what's going to happen in our definition, easy definition? 20 Newtons. Okay, so these values are changing, but the reality remains the same. The cause-effect relationship does not change. Okay, it still follows that if the mass is doubled, force is also going to get doubled. Okay, both will happen together. So you can choose the value of k to be 1. Okay, so F equal to delta p by delta t. Okay, and if you take the calculus version of this law, it will be F equal to del p by dp by dt. Okay, d by dt, which means the instantaneous rate of change of this new quantity called momentum. Okay, so yeah, so for the most common use case that we have, when we know, we write this as this, but you have just learned that this is nothing but this. Okay, for most cases the mass of the body we are considering is going to be a constant. Okay, mass is going to be a constant. So what we can do is get this out of the derivative or the change and write like this. And you know what the rate of change of velocity is, nothing but acceleration. So this becomes F equal to ma. This is the famous law that we have been using, and now you know from where we can sort of make sense of this. And yeah, we'll apply it in a lot of problems and see that it makes sense in the real world and strengthen your belief on it from the next modules. And the first thing we're going to talk about is how do we identify the forces on a body. Okay, because F in this equation is just about the cumulative effect of the forces. It doesn't talk about which forces. Okay, and that's what we're going to discuss in the next module.